Chapter 4, Types of Chemical Reactions and Solution Stoichiometry. Our outline is water and dissolving, strong and weak electrolytes, concentration, molarity, precipitation reactions, acid-base reactions, redox reactions. Alrighty, so our first area, water and dissolving. Water is polar. Polar compounds have a separation of charge, but are neutral overall. This diagram here shows a model of water. It shows the shape of water. You know water is H2O, so there's two H's, one O. It's a bench shape. We have oxygen with hydrogen coming off at in a bench shape. The oxygen end has a partial negative charge and the hydrogen end has a partial positive charge. And that is always there. Water is polar. It has a permanent separation of charge. All polar compounds have a permanent separation of charge. The bonds are covalent, formed by a sharing of electrons from oxygen and hydrogen atoms. But the electrons are not shared equally between O and H. If they were, the number of protons in the nucleus would equal the number of electrons around it. Oxygen wants electrons more than hydrogen does, so oxygen has a partial negative charge, which we symbolize with that Greek symbol delta, delta minus, and hydrogen has a partial positive charge, delta plus. The delta just implies not a full charge, just a portion of a charge. In water, the delta plus is 0.2, the delta minus is negative 0.2. So it's that portion of a full charge. The dissolving process. Many compounds dissolve in water. The solute, as we call it, the one dissolving in the water, the solute is the compound present in smaller quantity, and the solvent is the compound present in the larger quantity. So imagine we're dissolving a little bit of sodium chloride in water. So the water is the main one there, it's the solvent. The sodium chloride is the solute. The solution is the homogeneous mixture of the solute and the solvent. So it's it's the same throughout. The solution, it's see-through. We don't have chunks of undissolved solute in part of it, like in the bottom of the cup. It's all throughout. It's called a solution. Here's a picture of the dissolving of an ionic compound like sodium chloride in water. So the NaCl is represented by the lattice structure with the green and gray balls. The green would be the Cl minus, the gray would be the Na plus ions that are bonded together through the ionic bond. The water is depicted as the bend structure with the oxygen, the red ball representing O, and the blue balls on the sides of it representing the hydrogens. The negative end of water interacts with Na plus, and the positive end of water interacts with Cl minus, causing NaCl solid to dissolve in water. The dissolving can be shown as NaCl solid dissolving in water, so water's over the yield sign, to yield Na plus aqueous plus Cl minus aqueous. We could make that a little bit more compressed by writing NaCl solid in water, over the water over the yield sign, yielding NaCl aqueous. What that NaCl aqueous implies is we have the Na plus surrounded by water, separate from the Cl minus, which is also surrounded by water. So instead of writing Na plus aqueous plus Cl minus aqueous, we can simply write NaCl aqueous, and that means the same thing. The strong Na plus dash Cl minus ionic bond separates as weaker but very plentiful water ion bonds form. Notice in our picture of this dissolving process, we have several water molecules surrounding each anion and each cation as the water just kind of pulls away those ions, brings them into solution, and they aren't together anymore, so that we see what looks just like water, but of course is sodium chloride dissolved in the water. We just don't see the sodium chloride anymore because they're all separated from each other, the sodium cations and the chloride anions. So the ions separate from one another as they get surrounded by water. That is to say, they get hydrated. So that process is called hydration, this dissolving process. Water dissolves many ionic compounds, such as NaCl, but not all. Here's some ionic compounds and their solubility in water at 25 degrees Celsius. So we have RbNO3, and what that 65.0 represents is the grams of that solute that would dissolve per 100 mLs of water. So a lot, we call that soluble. It would become aqueous. KCl, 35.5 grams per 100 mLs of water, it is soluble. The lithium carbonate, Li2CO3, not as much will dissolve, 1.30. Some will dissolve, certainly, but not a lot. We could call that soluble, but to be more descriptive, we might call it only slightly soluble. Calcium hydroxide, 0.160, not much, so definitely we would refer to that as slightly soluble. Barium sulfate, 0.00031, very small number, so insoluble. Same with the magnesium phosphate. From pattern recognition, so from observing many, many ionic compounds, we have what are referred to as solubility rules, or with more description, aqueous ionic compound solubility rules. So we're talking ionic compounds dissolving in water. An ionic compound is soluble, that is aqueous with water, if it contains cations that are from group 1A on the periodic table. That would include the lithium, sodium, potassium group, or if it contains ammonium as the cation. So if we see those, we would call it soluble for the most part, aqueous. If not one of those cations, well, then we would go to the next list for anion part of the compound and see if we can determine anything from the anion. So it is soluble if it contains group 7A halide ion. So that includes the fluorine, chlorine, bromine, iodine group, except when the halide ion is combined with Ag+, Cu+, Hg2, 2+, or Pb, 2+. If it contains nitrate, NO3-, or nitrite, NO2-, or chlorate, ClO3-, or perchlorate, ClO4-, or acetate, acetate is C2H3O2-, except when acetate is combined with Al3+ or Ag+. or if it contains sulfate, except when sulfate is combined with Ca2+, Sr2+, Ba2+, Pb2+, or Hg2 2+. So if not one of those cations we refer to, or one of those anions, except of course with all their exceptions, we think it's probably insoluble. It would probably not dissolve in water, at least not to a significant extent. So based on those rules alone, here's an example. Is each compound soluble, aqueous, or insoluble? That is, stays a solid in water. So let's look at the first one, CuCl2. Okay, so what we have is Cu2 plus, Cl minus here. So looking down our solubility list, well, the cation, it's not a group 1A ion, it's not ammonium. Remember, ammonium is NH4 plus, so that doesn't help us. So let's go to the anion list. It is a group 7A halide ion, and we have that Cu2 plus is not one of the exceptions, so we would say aqueous. Okay, so come back later and do that example. Dissolving of polar compounds like ethanol in water. Ethanol is the alcohol in beer, wine, vodka, etc. So ethanol is shown in diagram A. It's C2H5OH. It has an OH group. That's a lot like the OH portion of water. And in that sense, the O is partially negative charged, the H is partially positively charged. It is a polar molecule, and it can interact well with water. So this polar bond, this OH bond of ethanol, interacts strongly with water and makes ethanol completely soluble in water. And think about that. Have you ever seen a layer, a separate liquid layer in beer or wine, or like a stronger drink like vodka? No, it's all dissolved in the water. Soluble polar compounds separate from one another as they get surrounded or hydrated by water. So we could symbolize ethanol dissolving in water as we are seeing here. C2H5OH liquid, because it's a liquid at room temperature, dissolving in water, forming C2H5OH aqueous, meaning it's still intact as a molecule. The molecule is not breaking down, like the NaCl becomes Na plus Cl minus, separated from one another as they go aqueous. That doesn't happen with ethanol, but it does get surrounded by water molecules, so we no longer have ethanol, a clump of ethanol molecules together. Water dissolves many polar compounds like ethanol, sucrose, glucose, lots of polar compounds. Nonpolar compounds like fat and oil do not have a permanent separation of charge. They do not interact well with water and therefore do not dissolve in water. Water does not dissolve nonpolar compounds. Nonpolar compounds dissolve in nonpolar solvents. Like we can dissolve fat and oil in some kind of a nonpolar solvent. This can be summarized as like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. All right, our next section is strong and weak electrolytes. A solution can be described many ways. For example, by what it contains, like maybe it's a sodium chloride solution, whether it's concentrated or dilute. Do we have a lot of sugar in our tea or just a little bit of sugar in our tea? It can also be described by its electrical conductivity, and that's what we're focused on in this section. So what we have in those diagrams is a light bulb that's plugged into an outlet, and it has two probes sticking into an aqueous solution. If the probes can conduct electricity, then the light bulb will glow. And we call that the circuit being complete. In our first picture on the left, we see the glowing light bulb because the circuit is complete. The circuit is complete when there are ions, that is, charge carriers, in the aqueous solution. The more ions there are, the more conductivity there is, the brighter the glow we get. So in our first example, we have a bright bulb. Below it, we see what's in the solution. We see that it contains ions. It contains the green negative ions, the blue positive ions. We have that when we dissolve compounds like NaCl or HCl in water. They make for lots of ions in solution, so good conductivity, a bright light bulb. When we dissolve an acid like acetic acid, we do get a bit of a glow, but not much. And that's because although acetic acid does dissolve in water, it only forms a few ions. We see that in the picture shown. We see one plus, we see one minus. Those other molecules are the whole acetic acid together. So a little bit of acetic acid breaks down to ions, but most of it does not. But it does dissolve in the water. We would see only one solution. Some compounds dissolve in water, like ethanol, as we talked about. Sucrose does so in a very similar way, but they do not make ions. So yes, they dissolve, but no ions. We see no conductivity, no glow on our light bulb. Alrighty, so more on what's going on here. When NaCl dissolves in water, we get Na plus aqueous plus Cl minus aqueous. And what I have in that row right below, where the row has the header I, that I is initially. If we could get on the microscopic scale and count out 100 NaCl's and dissolve them in water, we would find that our final amount of Na plus is 100. Our final amount of Cl minus is 100. So what I have for those two I and F rows are, initially, we have only NaCl solid. We have no Na plus, we have no Cl minus that are aqueous. And then, after they all dissolve, the final state is no more NaCl solid, but 100 Na pluses aqueous, 100 Cl minuses aqueous. A beaker representation of that we could draw like I've drawn there. We have Na plus, we have it separate from Cl minus, and we have a bunch of those in there. Hydrochloric acid, HCl, it's a gas at room temperature. When we bubble it into water, we get H plus aqueous plus Cl minus aqueous. If we start with 100 HCl molecules, we have no H plus or Cl minus initially until we dissolve them in water, and then after they dissolve, we have no more HCl gas, but we have 100 H pluses and we have 100 Cl minuses. They completely ionize. So we have hydrochloric acid completely ionizes. Hydrochloric acid is what we would call a strong electrolyte. It makes for a strong glow. Go back up to the NaCl example. Because NaCl completely ionizes, separates into the ions, it's termed a strong electrolyte. Makes for a strong glow. Now go back to the HCl stuff. HCl is an acid. It's called hydrochloric acid. We can hear that in the name. Acids are proton donors, so they form H plus. We can call H plus a proton because H, the atom, has in its nucleus only a proton, and in its electron cloud an electron. If we remove the electron and thus have H+, we only have a proton left behind. So acids make for H+, they create that, and that could be donated to something else, something that it will react with. So acids are called proton donors. Strong acids completely ionize. Well, if we look at our numbers over there, it's completely ionizing. All 100 HCl's goes to 100 H pluses and 100 Cl minuses. So HCl is what we call a strong acid. It turns out we have a few strong acids and we have many, many, many weak acids. The strong acids I want you to know of are HCl, HNO3, nitric acid, H2SO4, sulfuric acid, HClO4, perchloric acid, HBr, hydrobromic acid, and HI, hydroiodic acid. So go back to the beaker representation. So what we would have in our beaker is H plus and Cl minus floating around, each surrounded by water. And then here is acetic acid. That's the one that makes for a glow, but not much of a glow. Acetic acid is HC2H3O2. It's a liquid at room temperature. It readily dissolves in water, so it separates into its individual molecules. If we dissolved 100 of those in water, we'd find, yes, they all do become aqueous. And of that bunch, only about one acetic acid molecule ionizes to H plus aqueous plus C2H3O2 minus aqueous. So acetic acid, though dissolves, does not completely ionize. It's what we would term a weak electrolyte. We can see a bit of a glow in the light bulb. Well, it's an acid, and because it does not completely ionize to H+, it's what we would term a weak acid. Also, it's not on our list. What's on our list is these 6 acids. If it's not on that list, you can assume it is a weak acid. In our picture representation, our beaker representation, we would show that we have most of our molecules, when they're dissolved, looking like HC2H3O2, with very few being broken down to H plus and C2H3O2 minus. Ethanol, so ethanol, which again is C2H5OH, it's a liquid at room temperature. It readily dissolves in water. If we dissolved 100 of those molecules, we would find that we have 100 that are surrounded by water, so that are aqueous, but they're not broken down. Ethanol does not ionize. In our beaker representation, we have just those individual molecules surrounded by water. It is a non-electrolyte. It would not make the light bulb glow. Molecules tend not to break down. Here is sucrose, C12H22O11. It's a solid, as you know. At room temperature, we can readily dissolve it in water. It just gets surrounded by each individual molecule surrounded by water. So we have, once dissolved, C12H22O11 aqueous. It does not ionize. If we dissolve 100 of those, they will become aqueous, but they will not ionize. It's a non-electrolyte. Sodium hydroxide is a solid at room temperature, and it dissolves readily in water, and it forms Na plus aqueous plus OH minus aqueous. If we counted out 100 NaOH solid units, of course we'd have to be on this make-believe microscopic scale, we would find that when they dissolve, we have 100 Na plus aqueous and 100 OH minus aqueous. So our problem here, and come back to it later, is draw the beaker representation. So what's in the beaker? Decide if NaOH is a strong, weak, or non-electrolyte. Would the light bulb be bright, dim, or not glow based on its electrolyte properties? Some new information is bases produce OH minus in solution, at least bases that we will talk about this semester. They produce OH minus in solution. Strong bases completely ionize. Well, based on our numbers there, we see that NaOH completely ionizes, and it is a base because it produces OH minus, so NaOH is a strong base. KOH is another strong base. Our next example is AgCl solid in water. Well, it really does not dissolve. It's one of these insoluble salts. And so what would we have? Would the light bulb be bright, dim, or not glow? Contrast the light bulb brightness with NaCl. Here's another example for you to come back to later. Draw a beaker representation of the major solute particles in each aqueous solution. For acids, show several solute particles so as to distinguish between weak and strong acids. So we have HClO4 perchloric acid, so that's an acid. You'll have to check whether that's on the strong acid list. If so, you hopefully know how to deal with it. Propanoic acid, so it's also an acid. Check out whether it's on that list. Glucose is a molecule. It's like sucrose. Here's another problem for you to come back to later. Rank these compounds in order of increasing conductivity. So we have BaCl2. Look at the solubility rules. Think about whether it's soluble. If so, how many ions does it break down to? Think about the light bulb. Would it be bright or dim, etc.? Methanol, that does readily dissolve in water. Think about whether it becomes ions. Compare it to ethanol. And our last one is carbonic acid. So check out whether it's on that list. Decide about how many ions it forms in comparison to the other two. So in that sense, rank them from the dimmest glow to the brightest, because that's in order of increasing conductivity. Our next section is on concentration, and there are several concentration units that we will use this semester. This first one that we'll be introduced to in Chapter 4 is molarity. Probably that's our most common concentration unit in chemistry. So we can have concentrated solutions, like we see the most blue one there on the left, that's the most concentrated, and then we see it's getting less blue as we go to the right. So we're going from concentrated copper 2 nitrate down to a diluted solution of copper 2 nitrate. And it turns out those concentrations are, for the one on the left, 1 molar, and the one on the right, 0.05 molar. So that M there is the molarity, the concentration unit. So concentrations can vary. Molarity is defined as the moles of the solute per liter of solution. The units of molarity are molar, like up there we have 1 molar solution, we have 0.05 molar solution. We can write a big M when we're writing that out. The units break down to moles per liter. So how do we prepare a solution? So we weigh out the amount that we want, and we put it into the flask. That's that orange compound in diagram A. We put it into a flask that is marked in the skinny part of it so that we can accurately add the right amount of water to it to get it to be the solution volume that we want, the liters of the solution that are in the bottom of the molarity equation. So we put some water in, we shake it up, and then we fill up to such that the bottom of the meniscus is right at that line. Our example here is, what is the molarity of a solution where 75.0 grams of NaCl are dissolved in enough water to give 300.0 mLs of solution? Okay, so molarity is moles per liter, moles of the solute per liter of solution. So for what we have in the numerator is going to be the moles of the NaCl. So we take our 75.0 grams, we divide by the molar mass of NaCl, which is 58.44 grams per mole. Notice we wrote it in a way that the grams cancel out. We're left with moles in the numerator. And then in the denominator, we put the liters of solution. So we take our 300.0 mLs, convert to liters. Notice mLs over mLs, they cancel. We're left with liters. So once we've done all that division and so forth, we get the molarity to be 4.28 molar. Remember that we used density as a conversion factor. We can calculate density, mass per volume. We can also use density if we're given it to jump between mass and volume in a calculation. Well, in the same way, we can do that with molarity. We can jump between moles and volume with molarity. It's like the bridge. So here's an example. We have 25.0 mLs of 4.28 molar NaCl solution. How many moles and how many grams of NaCl are there? Alrighty, so we're going to be using the molarity as a conversion. Now, molarity has liters in it, so first off, we have to convert our 25.0 mLs into liters. And then we write the molarity such that we have liters in the bottom, so they'll cancel with the liters in the top, and we're left with just moles. So we take 25.0 mLs, we divide by the 1000 mLs per liter, we multiply by 4.28 moles per liter, and we get 0.107 moles of the NaCl. How many grams is that? Well, then we take the moles, we convert to grams using the molar mass. We write everything so units work out, and we get 6.25 grams of the NaCl. So here are two examples for you to come back to later and do. Our next section is dilution. So the stockroom buys concentrated solutions and dilutes them to desired concentrations later as needed using the dilution equation, which is M1V1 equals M2V2. It turns out that that equation is saying that the moles of the solute before dilution equal the moles of the solute after dilution. Moles equal moles, so that's what that's based on. Okay, so in our dilution equation, M1 and V1 are the molarity, M1, and volume, V1, of the initial concentrated solution. M2 and V2 are the molarity and volume of the final diluted solution. So here's an example of how we dilute a solution. We have how to make 5.00 liters of a 1.50 molar KCl solution from a 12.0 molar stock solution. Using the dilution equation, we would determine the amount of the initial concentrated solution we need. In fact, let's go determine that and then we'll come back. Okay, so here's our example. We want 5.00 liters of 1.50 molar KCl and have 12.0 molar KCl. So we want to dilute it, and we want 5 liters. We will use the dilution equation to calculate the volume of the 12 molar KCl that we will dilute to 5 liters. All right, so we have M1 is 12.0 molar. V1 is what we're after determining. So V1 equals question mark. M2 equals 1.50 molar. And V2 equals 5.00 liters. So there's our dilution equation. M1 V1 equals M2 V2. We're after V1, so we rearrange that equation to solve for V1. V1 equals M2 V2 over M1. Putting in our numbers, V1 equals 1.50 molar times 5.00 liters divided by 12.0 molar. So we see molar cancels out, we're left with liters, and we calculate V1 to be 0.625 liters. Okay, so now we go back up here, and we, in that volumetric flask, we measure out 0.625 liters. We put it into a flask that has the mark right at 5 liters. So we're pouring in our 0.625 liters of our 12 molar stock solution. And then we add water to that such that we get the bottom of the meniscus right at that 5 liter mark. And now we have 5 liters of 1.50 molar KCl. Now down here is a justification of that equation. So our dilution equation is M1 V1 equals M2 V2. So if we have our 12.0 moles per liter times 0.625 liters, notice the liters cancels out. We only have moles on the left side. We have 1.50 moles per liter times 5.00 liters. So again, we have liters canceling out. When we do the multiplication, we end up with 7.5 moles equals 7.5 moles. What that means is, what was the moles of KCl that were dissolved in water in our concentrated solution, what are in this volumetric flask that gets poured into our big flask, that was 7.5 moles. Now, that's all the moles of the KCl that we have in there. But we've diluted it with water, so we have a bigger quantity of solution, but the same number of moles. Here's an example for you to come back to later. Our next section is precipitation reactions. These are reactions where the reactants are aqueous ionic solutions. That means see-through ionic solutions. And a precipitate, a solid, is produced. Okay, so in our picture there, Ki aqueous is being mixed with PbNO3 aqueous. Notice that we have a beaker. Ignore the yellow part. Look at the see-through parts. We have the aqueous solution. Let's say that's our lead nitrate. So it's that aqueous ionic solution, one of the two we're starting with. And then we have a flask where you can see the liquid being poured out of it. It's also see-through. So that would be, for example, the Ki. When those two get together, they form a precipitate, a solid. They're forming that yellow solid. That solid would eventually settle down to the bottom of the beaker and look less like just kind of a cloudy emulsion. It would look like a solid. So looking at our reaction, we have Ki aqueous, we have PbNO3 aqueous. What those are really are K plus aqueous plus I minus aqueous. Now those two are a solution. They don't make a precipitate. The PbNO3 are also ions that are separate from each other. They don't make a precipitate. So we have Pb2 plus 2NO3 minus. But when we mix those 4 ions together, they make a precipitate, that yellow precipitate. Let's look at what could be causing it. Well, certainly those ions before mixing don't make a precipitate. Let's look at all other possible combinations. K plus won't like Pb2 plus. They repel each other because they both have plus charges. The I minus won't like the NO3 minus because they repel each other. What about the K plus and the NO3 minus? Maybe they make a precipitate. At least they've got opposite charges. What about Pb2 plus and I minus? Maybe they make a precipitate. So what we do in deciding what forms is we follow these steps. So we exchange the partners. We put K plus with NO3 minus. We put Pb2 plus with I minus. We always write the cation first, then the anion, and we write the ionic compound so it is neutral. So with the lines there, I'm trying to show put the outside ions together, put the inside ions together, and write them so they are neutral. K plus, NO3 minus, they're on a 1-to-1 ratio. Pb2 plus, I2 minus, they're going to be on the 1-to-2 ratio because of their charges. So we have KNO3 plus PbI2. Then we balance the reaction with stoichiometric coefficients. So we put the numbers, or the invisible one, in front of the compounds. So because we have 2 i's on the right side, we'll put a 2 in front of the Ki on the left side. Because of that, we have to put a 2 in front of the KNO3 on the right side to balance the potassiums. So now it's balanced. Notice we put aqueous beside our 2 reactants because that's how they begin. And then we use those aqueous ionic solubility rules to decide if a solid S or an aqueous AQ solution forms. So aqueous means the cation and the anion are soluble, the liquid is clear, might have a color, but at least it's see-through. And an S means the cation and anion are insoluble. The solution is cloudy, or we see the solid at the bottom of the beaker. When we look at the solubility rules, we see, okay, cations, group 1A. Well, K is from group 1A, so automatically we say that's aqueous. The Pb is not group 1A, it's not ammonium, so we have to go to the anions to see if we can learn anything. Well, I minus is a group 7A halide ion, and we have that those are soluble except when the halide ion is combined with Ag plus, C plus, Hg2, 2 plus, or Pb2 plus. Well, there it is, so we know it's a solid. So our overall reaction is that 2Ki aqueous plus PbNO3 aqueous yielding 2KNO3 aqueous plus PbI2 solid. So the yellow solid we saw is PbI2. So let's combine an aqueous solution of sodium sulfate, Na2SO4 aqueous, and an aqueous solution of barium nitrate, BaNO3 aqueous. Going through the rules, we get this precipitation reaction. So we exchange partners, NaNO3 plus BaSO4. We balance, we need a 2 in front of the NaNO3. And then we look at the solubility rules to determine that the sodium nitrate is aqueous and the barium sulfate is a solid. So that would be our reaction. Looking at more details of what's really happening, we can picture it with our beaker representation. The Na2SO4 aqueous, we would write Na plus, SO4 2 minus. We're keeping the ratio. We have 2 Na pluses for every SO4. The BaNO3 is Ba2 plus then the 2 NO3 minuses separated from one another. In our product beaker, we have, because we have two NaNO3 aqueous, we have Na plus, Na plus, NO3 minus, NO3 minus in our solution. And then in the bottom, we have the BaSO4 solid. So when we write the reaction as what we've written above, that Na2SO4 aqueous plus BaNO3 2 aqueous yielding 2 NaNO3 aqueous plus BaSO4 solid, that's called a molecular equation, or maybe we could call it a formula equation. It shows all reactants and all products, all the details. Another way to write the equation is that net ionic equation. Net meaning it's gotten rid of some stuff. It does not include ions that are unchanged. They are the same on both sides. These ions are called spectator ions. They're just kind of watching what's going on. They're not participating. In our case, the spectator ions are Na plus and NO3 minus, because notice in our beaker representation, we have two Na pluses and two NO3 minuses on the left side, and that's basically the same. We have the two Na pluses, we have the two NO3 minuses on the right side that are all just aqueous. Those are the spectator ions, and we leave those off. So our net ionic equation is Ba2 plus aqueous. We had to leave the NO3 minus off, so we have to now write Ba2 plus SO4 2 minus. So again, we left off Na plus, so we have to include the charge, the 2 minus charge. That yields BaSO4 solid. So our net ionic equation is Ba2 plus aqueous plus SO4 2 minus aqueous yielding BaSO4 solid. Another way to write the equation is the complete ionic equation, where we've just separated everything that is separated. It takes a lot more writing. We tend to show either the molecular, the formula equation, or the net ionic. So here's an example for you to do with lithium carbonate and aluminum chloride. Draw the beaker representation also. Here's another problem for you to do. And of course, the answers are in the back. If no solid forms, there is no net ionic equation. There is no net change. Later on, go through the rules. Take this KC2H3O2 and combine it with CaNO3 so aqueous solutions of those, come up with the full molecular equation. So you exchange partners, you get KNO3 and you get CaC2H3O2, and then balance, you need some 2's in there, and then check the solubility rules. You'd find both of those are aqueous. So there's no solid that forms. The beaker representation would be, as I've shown there, just a bunch of ions on both sides. They cancel out, right? We have as many calciums on the left as the right, nitrates on the left as right, and so forth. So there is no net ionic equation. Now we will talk about stoichiometry, calculations using precipitation reactions. So to do these, you run through these general rules in this order. You write the balanced molecular equation, including aqueous and solid and all that, include everything, balance it, etc. And then calculate the moles of the reactants you have. Usually you're given amounts of the two reactants. Because you have amounts of both, you have to identify the limiting reactant. And then you calculate the moles or grams of the product from that limiting reactant. So we will do an example of this sort in this problem here. 0.25 liters of 1.0 molar AlCl3 aqueous and 0.25 liters of 2.0 molar NaOH aqueous are mixed. If a precipitate forms, how many grams are obtained? Okay, so what we do is we write out the reaction, we go through the rules, we exchange partners, we do the balancing, we look at solubility rules, we would find that our molecular equation, and definitely make sure that you could come up with this on your own, is AlCl3 aqueous plus 3 NaOH aqueous yields AlOH3 solid plus 3 NaCl aqueous. So now we have to figure out the moles of each reactant. So we take our volume, 0.25 liters, and multiply by molarity. For the first reactant, it is 1.0 moles aluminum chloride per liter. So we get 0.250 moles of aluminum chloride. For the second reactant, we have 0.25 liters times 2.0 moles NaOH per liter. We get 0.500 moles of NaOH. So to determine which is the limiting reactant, we take the smaller of the two, 0.25 moles of AlCl3, and we determine how much of the other reactant we would need to react all of those 0.25 moles. So 0.25 moles AlCl3 times the ratio 3 moles NaOH per 1 mole AlCl3, we would need 0.750 moles of NaOH to use up all of that aluminum chloride. Well, we don't have that. We only have 0.500 moles of NaOH, so that makes NaOH the limiting reactant. So we finish up our calculation with it. So we take our 0.500 moles of NaOH that we have, multiply by the mole ratio between the NaOH and the aluminum hydroxide, 1 to 3, and then we go from moles of aluminum hydroxide to grams of it. Its molar mass is 78.01 grams per mole, and we would calculate the value 13 grams of aluminum hydroxide are obtained. Here's an example that you should come back to practice doing this kind of a problem. So make note to come back to that. Its answer is right there, but we have not gone over it together, so come back to it. Our next type of reaction is acid-base reactions. So using an acid-base definition called the Bronsted-Lowry definition, we have that an acid is a proton H+ donor. We saw that before. And before we saw that the strong acids that I want you to know of are these 6: hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, nitric acid, and sulfuric acid. Weak acids are all others. This weak acid, HC2H3O2, is acetic acid. All others that aren't of those 6 we assume are weak acids. And recall that weak acids do not completely ionize in water. They form some H+, but not entirely. Most of them just dissolves in the water to keep their complete molecular structure. A base is a proton acceptor. So also a base forms OH- for us. The OH- likes H+, and in that sense OH- is a proton acceptor. H+ plus OH- forms water. When an acid and a base are reacted, the reaction is so favorable that lots of heat is generated. The general acid-base reaction is acid plus base yields water plus salt. So here's an example. Write the acid-base reaction equation of hydrochloric acid and potassium hydroxide. Also write the net ionic equation. Alrighty, so we have HCl aqueous plus KOH aqueous. As we did with the precipitation reactions, we're basically exchanging partners. The H+ and the OH- combine to give us water, liquid water, and the K+ and the Cl- combine to give us the KCl. And if we look at the solubility rules, we'll see that KCl is aqueous. This reaction is also called a neutralization reaction, since very reactive HCl and KOH are now unreactive salt and water. The powerful acid and base have been neutralized. So a beaker representation we would have for that strong acid H plus and Cl minus. We would have K plus and OH minus for the base. And in our product beaker, we have aqueous K plus, Cl minus, and we have water. So if we get rid of spectator ions, our net ionic equation is H plus aqueous plus OH minus aqueous, yielding H2O liquid. So in this example, we write the acid-base reaction equation of acetic acid, which is a weak acid, and NaOH. And write the net ionic reaction also. So so we exchange the partners. We put the Na plus with the C2H3O2. They're on a 1-to-1 ratio, so we have just Na C2H3O2. By the way, that's aqueous. I left that off. Make that aqueous. It follows just from the solubility rules. Na plus is group 1A ion. The H plus and the OH minus make liquid water, so everything's on a 1-to-1 ratio, so that's our molecular equation. Now, what we have in our beakers, we have for the weak acid, most all of it is just the molecule H, C2H3O2. Most all of it is that. And in our beaker representation for the base, we have Na plus separate from OH minus. When they combine in our product beaker representation, we have Na plus and C2H3O2 minus. Those are in the solution part, and then water is in the is formed. So canceling out spectator ions, all we have as a spectator ion is Na plus. That's the only one that's the same on both sides. So our net ionic equation is C2H3O2 aqueous plus OH minus aqueous, yielding C2H3O2 minus plus H2O liquid. A little different when we have a weak acid involved. Okay, I have a couple examples for you to come back to later. Now we'll do a calculation, an acid-base titration type calculation. So what we have is HCl in the flask, shown, it's that colorless solution in the flask, in the Erlenmeyer flask. And then we have a burette, which is a long, skinny piece of glassware that has a stopcock at the bottom. When we put liquid in it, we can open it and let liquid from the burette out. Also on the burette, we have graduation marks, so we can determine the amount of liquid that we have used. In our example here, we have NaOH in the burette, HCl in the flask. Our problem is, what is the concentration of the HCl solution, that original one in our flask, if it takes 37.50 milliliters of 0.100 molar NaOH in the burette to neutralize 25.00 mLs of it. So what we have then is, in our flask we have 25.00 mLs of HCl. We're after what its concentration is. We're adding to it 37.50 mLs of 0.100 molar NaOH that are in the burette. How do we know when we've added enough to neutralize it? We have an indicator in the flask that turns just slightly a pink color when we stop the titration, when we stop adding NaOH. This is, by the way, a titration type experiment. So NaOH is in the burette, HCl is in the flask. Our reaction is HCl plus NaOH yielding water plus NaCl, everything on a 1-to-1 mole ratio. Alrighty, so 1-to-1 mole ratio. What we know a lot about is NaOH. We know how many mLs of it are used. We know its molarity. So what we will do then is determine the moles of NaOH, and then we will jump from moles of NaOH to moles of HCl, and then we want the molarity, so we will divide the moles of HCl by the volume of the HCl. Alrighty, so we take our 37.50 mLs of NaOH, we convert that to liters, and then we multiply by the molarity of the NaOH, 0.100 moles NaOH per liter. Now we're at moles of NaOH. Then we use the mole ratio to jump from moles of NaOH to moles of HCl, 1-to-1, and we have 0.00375 moles of HCl in our flask initially. Molarity is moles per liter, so we take those moles and we divide by the liters of the HCl. Remember, there were 25.00 mLs of it, so we have to convert that to liters. Divide that all into the moles, and we get that the original molarity of the HCl was 0.150 molar. Here's a problem that I will talk about a bit, and I'll want you to come back to and work on. What is the concentration of NaOH if 0.1082 grams of KHP, that's an acid, with a molarity of 204 with a molar mass of 204.22 grams per mole, are required to neutralize 37.67 mLs of it. So what we have is NaOH in the burette, we have KHP in the flask, we've dissolved 0.1082 grams of it in water, and we add the NaOH to it until we just get the pink color, and we see that the amount of NaOH we're adding is 34.67 mLs. Okay, so I've shown you what the reaction is between the KHP and the NaOH. So KHP has one H+, so they're on a 1-to-1 mole ratio. And so we go from grams of KHP to moles of KHP, then we jump to moles of NaOH with the mole ratio. Now we have moles of NaOH, we divide by the volume of it that we used, and we get the molarity of the NaOH. So come back and do that problem later. Here's another example for you to do later. Our next section is on the last kind of reaction we'll talk about, the redox reaction. Redox reactions involve the transfer of one or more electrons between reactants. So let's go back. Precipitation, two aqueous solutions that give us a solid. Acid-base, we have an acid combined with base to give us salt and water, a neutralization reaction. Redox reactions involve transfer of electrons. Okay, so let's say we take a copper sulfate solution, put it in a beaker. We're going to see it's a blue solution. And we put a piece of zinc metal into it. After a little while, we would see that the blue color has definitely gone down, and we would see that stuff is starting to form on the zinc. Well, it turns out the reaction that is occurring is zinc solid plus copper 2+ aqueous, yielding zinc 2+ aqueous plus copper solid. That would be the net ionic reaction. The sulfate is not changed. What we have is zinc, the atom, has gone to zinc 2+ the ion, and we have copper 2+ the ion has gone to copper the atom. the copper 2 plus, that's what makes for that blue solution. Well, if we have less of it, we get a lessening of the color. And the copper solid that's forming is plating onto the zinc metal. So if we were to rub off all that copper solid, we would find that the zinc strip weighs less after than it did when we first stuck it into the copper sulfate solution. The zinc atom has gone to zinc 2 plus by giving up 2 electrons. The copper 2 plus has taken on those 2 electrons to give us copper, the atom. These two reactions combine to give us our overall reaction, zinc plus copper 2 plus yielding zinc 2 plus plus copper. These are, we could call them half reactions. They add up to give the overall reaction. The reaction of redox reactions, because here we have a redox type reaction, we have electrons involved. The half reaction that gives up electrons is called the oxidation half reaction. The reaction that takes on electrons is called the reduction half reaction. The oxidized reactant loses electrons. That's the zinc. Its oxidation state increases. Oxidation state, or we could call it oxidation number, is for that half reaction. We have 2 oxidation states. We have zinc, the atom with no charge, so its oxidation state is 0, going to zinc, the ion, with a 2 plus charge. Its oxidation state is 2 plus. So we have oxidation that has occurred because 0 has gone up on the number line to 2 plus. Oxidation has happened. It has lost electrons. The reduced reactant, that would be the copper 2 plus, it gains electrons. Its oxidation state has decreased. It has reduced. That's where that term reduced comes from. The 2 oxidation states with that half reaction are 2 plus and 0. So 2 plus has gone down the number line to 0. It's been reduced. It has taken on electrons. The one substance was oxidized. Electrons were taken from it. It was oxidized by what we call the oxidizing agent. The oxidizing agent is the reactant that causes oxidation. It's the reactant that takes the electrons. The copper sulfate is the oxidizing agent in this case. The reducing agent is the reactant that causes reduction. It's the one that gives the electrons. That's the zinc. Oxidation states, so looking at the before and after values allows us to know if a redox reaction has occurred. So what we're going to do is talk about the rules for assigning oxidation states, which can also be called oxidation numbers. For an atom, the oxidation state is 0. So that would be like sodium, oxygen, O2, ozone, O3, or zinc or copper. Their oxidation states are 0. When we have a monatomic ion like Na+, like O2-, or like Zn2+, or Cu2+, the oxidation state is the ion's charge. When we have fluorine in the compound, its oxidation state is -1, like we have it in HF, in PF3. Its oxidation state is -1. When we have oxygen, its oxidation state is -2. So like in water or in CO. But when we have just pure oxygen, like in O2 or O3, its oxidation state is 0. An exception with oxygen is rare, but it's the peroxides. Its oxidation state then is -1. Hydrogen, if it's in a compound like water or HCl or NH3, its oxidation state is +1. the sum of the oxidation states is 0 for a molecule and is the charge for a polyatomic ion. So we calculate the oxidation state of unassigned atoms based on the above rules. So let's see how we do that. So, example, assign the oxidation state of sulfur in SO2. Well, oxygen, by our rules, has an oxidation state of -2. There's 2 of them, so the oxygen overall has a -4 oxidation associated with it. There's 1 sulfur, so to balance it, sulfur must have the oxidation state of +4. Sulfur in SF6, well, F is -1, there's 6 of those, so -6, so sulfur here must have the oxidation state of +6. Carbon in CO3 2-, so the 3 oxygens, each one -2, so the 3 of them -6. Now that overall polyatomic ion is -2. So what we have is -6, -2, so we have that that carbon must be +4. So carbon +4, oxygens, the 3 of them, -6, that gives the overall charge -2. So carbon here has a +4 oxidation state. Carbon in CO2, so each oxygen -2, we have 2 of them, so -4, carbon has +4 oxidation state here. Carbon in CH4, each H +1, there's 4 of them, +4, so here carbon has a -4 oxidation state. Okay, now how we use all that, we'll see in this example. In the reaction below, what atom was oxidized, what atom was reduced, which compound is the oxidizing agent, which compound is the reducing agent. Okay, so our reaction is CH4 plus 2O2 yielding CO2 plus 2H2O. So we have to look at oxidation states, and once we do that, we will see, yes, it's a redox reaction, and we will be able to determine what's oxidized and reduced and so on. Alrighty, so as we developed above, the carbon in CH4 has the -4 oxidation state, hydrogen +1, each one. The O2, each O has a 0 oxidation state. In CO2, each O has the -2 oxidation state, carbon +4. In water, each H is +1, the O is -2. Now we look at how the numbers have changed. Carbon went from -4 to +4, so it went up the number line. It's been oxidized, so we would say carbon was oxidized. Hydrogen +1 on both sides, so it's not changed. Oxygen is 0 going to -2. It's gone down the number line. It's been reduced. So O has been reduced. Always in a chemical reaction, something is oxidized, it gives up electrons, something else is reduced, it takes on electrons. Always we have electrons coming from something going to something. So one is oxidized while the other one is reduced. Oxygen caused the oxidation of the carbon, so O2 is the oxidizing agent. And the one that gave up the electrons is the CH4, so it's the reducing agent. Here's an example for you to do. We have the overall reaction, so determine if it's a redox reaction or not. Get the oxidation states of everything and determine what atom was oxidized, what atom was reduced, what compound is the oxidizing agent, what compound is the reducing agent. Our last example is to determine what types of reactions are occurring. So in our first reaction, we have copper plus silver nitrate forming copper 2 nitrate plus silver. And actually what that looks like is copper metal being put into a solution of colorless see-through silver nitrate. After a little while we start to see the blue color, and we can see the silver plating onto the copper. It's very pretty, sparkly, and you see it's a swirly design just based on the original shape of the copper wire. So decide what kind of a reaction is that. Our three choices are precipitation, acid-base, redox. The second reaction to work with is the calcium hydroxide plus HCHO2 aqueous forming the CaCHO2 aqueous plus H2O liquid. The last reaction to work with is the barium chloride plus the potassium carbonate forming potassium chloride plus barium carbonate. After that, we have just the answers. Alrighty, so go through these, your handout notes again, go through the video again, do the assigned homework, and yes, that's all for now.